Hello student, now I am going to discuss the state of the system. Last class I have started thermodynamics and now I am continuing from the last class. I have discussed types of system. Now I am going to discuss the states of the state of the system. Listen carefully, these concepts are also very important. Full thermodynamics is full of concept. You have to concentrate, you have to give full concentration. The system must be described in order to make any useful calculation by specifying quantitatively each of the properties such as its pressure P, that is denoted by P, volume V, and temperature T, capital V, and as well as fourth one, that is the composition of the system. The system must be described in order to make any useful calculation by specifying quantitatively each of the properties such as pressure P, volume V, temperature T, as well as composition of the system. These are the properties of the gases. And after that in physics, just you have to remember, in physics there two importance is given for two things. First, position, and second, velocity. In physics, you will find these things, importance of position and velocity, because with position, velocity is always changing, position and velocity. Okay, then here you have to, in chemistry, you have to give importance for, you can say, particularly in thermodynamics, a different and much simpler concept of the state of a system is introduced. It does not need detailed knowledge of motion of each particle. In physics it is given importance, but here no. Here in chemistry, particularly in thermodynamics, concept of a state of a system is introduced. It does not need detailed knowledge of motion of each particles, because we deal with average measurable properties of the system. B, specify the state of the system, also called state function. Both are same, state function or state variables. What are these variables? State variables. The state of a thermodynamic system is described by its measurable or macroscopic, that is also called bulk properties. Measurable or macroscopic properties is also called bulk property, BULK, bulk properties. Whole thermodynamics depends upon the bulk, not on few molecules, bulk, many, large number of molecules, on that it will apply. Now we can describe the state of a gas by quoting the pressure P, volume V, temperature T, and amount small n, etc. Variables, what are the variables? Now you understand. Variables are pressure, volume, temperature. These are called state variables or state function, because pressure will change. Here in thermodynamics, actually main importance is given for the initial state and final state. What change took place? Importance has been given in change, not in absolute. Change, what change took place? In pressure, how much change took place? In volume, how much change took place in temperature, how much this change took place. Then because these things are going to be changed from the pressure P1, it may change to P2. From the volume V1, it can change to V2. From temperature T1, it can change to T2. That's why it is called state variables or state function, because their values depend only on the state of the system and not on how it is reached, not on the path. Okay, only a state of system means initial state and final state, not on the path, how it is reached. In order to completely define the state of a system, it is not necessary to define all the properties of the system, as only a certain number of properties can be varied independently. This number depends on the nature of the system. This number depends on the nature of the system. Once this minimum number of macroscopic properties are fixed, other automatically have defined having definite values. As for example, if you know that relation PV is equal to nRT, then PV nRT. Then if you are knowing volume, you are knowing N, you are knowing R is universal constant, T you are knowing, then P you can calculate. Like that way V you can calculate if P you are knowing. Then like that way you have to fix some minimum number of macroscopic properties are fixed. Others automatically have definite values. The state of surroundings can never be completely specified. Fortunately, it is not necessary to do so also. The state of the surrounding, particularly surrounding, I am telling you, not the system. System is necessary, but the state of the surrounding can never be completely specified, and it is not required also. Now I am going to discuss the internal energy of a state. Internal energy is all in all actually. Now various type of energy is there, already I have told you. Here one more thing also, you know, work is also energy. I told you na, chemical energy, electrical energy, sound energy, light energy, and work is also energy. Work is also energy, don't forget. Okay, and its unit is given in joule, Joule, Joule. Okay, the internal energy as a state function, now we understand. When we talk about our chemical system means whatever you talk, suppose you are talking about the sucrose, means sugar, glucose, fructose, this is the system actually. What you are thinking, that is the system. Okay, this is the chemical system. We are telling it as a chemical system. System may be of various type. Okay, then here chemical system. When we talk about our chemical system, losing or gaining energy, we need to introduce a quantity which represent the total energy of the system. Total energy of the systems. It may be chemical, electrical, mechanical, or any other type of energy. Okay, and if you will make total, means sum of all these is the energy of the system, total energy of the system. If you will make sum of all this energy involved in the system, then that energy is called internal energy, and it is represented by U, capital U. This is the representation of internal energy. U means union. It includes all type of energy. Okay, in a system, whatever is possible, any type of energy, if it is there, you make it sum, total. And that is called internal energy of the system, and it is represented by U, also called U of the system, which may change. This U may change. Now this is again important things. This U means internal energy. Don't forget. In thermodynamics, 2-3 things you should not forget, because after that you can understand. Then some terms like that. U means internal energy. Always you will use this term U. Hence you should not forget. And slowly I will tell you what you should not forget. Always you remember when you are talking about the thermodynamics. Then now this U of the system, which may change. This U will change. When it will change, now you understand. Heat passes into or out of the system. If you will pass the heat into the system or it's go out of the system, that time U will change, internal energy will change. First thing, when heat passes into or go out or goes out of the system, that time U will change, internal energy. Second, when work is done on the system or by the system. Two type of work is done. This also you don't forget. Don't forget this. Work is done on the system or by the system. Both are meaningful. Okay. Now third, that matters enter or leave the system. If matters enter the system or leave the system, this three situation is common. Then when you will change. Okay. Matter, why will change matter? Actually, why internal energy will change, why the W? In work means W. That also don't forget. W means work done. Okay. Then why it will happen when work will be done on the system, by the system? On the system means positive. Okay. When work is done on the system, means compression is going on. Hence, W will increase. And because in doing the work, energy is required. Any work you will do, energy is required. You are compressing hand pipe. See how much pressure you are putting. Then water is coming up. Correct? Work you are doing, or you are pressing something in a cylinder, piston is there, or you are pressing it down. Suppose inside gas was there. Now you are putting pressure on the piston, it is going down. Then you are applying pressure. Then work is going to be done. Some work you are doing. Correct? Then sometimes for doing the work, system energy will increase. In this case, when compression is there, when you are applying pressure, then because you are applying the pressure, that's why work is going to be done, and that will be included in the total energy. Means total energy will increase. Recently, just in a reverse way, if work is done by the system, means it is just like that you are going to purchase some things. Then money you have to pay, then your money will decrease. Like that way, when system will do the work, then its internal energy will decrease, minus W. When system will do itself work, means expansion, like that, gas is expanding, that time energy will be required in expansion. Then system will expand that energy. That's why its internal energy will decrease. correct? Then in both cases I have told you, compression means just like someone is giving you gift, in gift they are giving you money, their money will increase. Then in compression same things happen, internal energy increases. When due to the external force it is going down, compression is going down, that's why internal energy will increase. Just like someone has given you gift, money or something they have given, then you became somewhat rich, like that situation is there. Then work is done on the system, by the system. On the system means positive, means it will increase, internal energy of the system will increase. And minus means they have incurred, they have spent, that's why there that will be minus, internal energy will be minus. Okay, that I have discussed what happened, meaning of a work done by, on the system, by the system, I told you. All are very important, only in the beginning I am telling you. Okay, and third one was matters enter or leave the system. Matters, see why matter, in matter also energy is hidden. How? You will tell how energy is hidden. Then now see, I am giving example. When you are breaking anything, wood you are breaking, or any small things you are breaking, then you are putting pressure. Why you are putting pressure? Because inside energy is there. Then you have to overcome that energy, then it will break. Okay, then in this wood is material, matter, then energy is hidden. Other things also you can, another example I am telling you, when you will burn the chips of wood, any small piece of wood or big piece wood also, if you will burn, then you are putting a small fire, but after burning it is giving too much energy it is giving after the burning. You have applied only a small quantity of heat. After catching fire it gives too much energy. It means that energy was hidden in that wood. Coal also same example. Anything we can take example which can burn. Okay, then matter involves has energy inside you can't see, but energy is, internal energy is there. That's why if matter will add, then energy will increase. If it will come to the system, matter will enter the system, its internal energy will increase. And if matter will go outside, then its internal energy will decrease. Then now I am specifically I am telling about the you can say work. Okay, work is energy, work energy, or simply work you can tell. Here some few terms are there, you have to understand. Okay, now I am telling about details about the work. Let us first examine a change in internal energy by doing work. By doing work, we take a system containing some quantity of water in a thermos flask. Suppose in thermos flask I taken water, or in an insulated beaker. Insulated beaker, no, that neither heat will enter, not it will go outside. This would not allow exchange of heat between the system and surroundings through its boundary, and we call this type of system as a adiabatic. Again important term, adiabatic means system which will not allow to go outside heat, or it will not allow to come from the heat come from outside, means from the surrounding it will not heat will not enter the system, and from the system it will not allow to go outside. That type of system is called adiabatic system. Okay, this is very important things, that it will not allow exchange of heat. In flask, already I told, in flask it will not allow anything, matter will also not go outside, Heat will also not go outside, means surrounding. From the surrounding also it will not enter into the flask. Then this type of system is called adiabatic. This type of substance is called adiabatic. Don't forget, Q is denoted for heat. Quantity of heat, it is denoted by a small q. Then here q is equal to 0. No entrance of heat, not leaving. Q is equal to 0. Okay. The manner in which the state of such a system may be changed will be called adiabatic process. The manner in which the state of such a system may be changed will be called adiabatic process. Okay. Then adiabatic process is a process in which there is no transfer of heat between the system and surroundings. Okay. Here the wall separating the system and the surrounding is called the adiabatic wall. What is the adiabatic wall? Now we have understood. Okay. This is the, again I am telling that adiabatic process is a process in which there is no transfer of heat between the system and surroundings. Here the wall separating the system and the surrounding is called adiabatic wall. Okay. Now you understand that this work, it can be done. Already I briefed you, but now again I am telling you, because in a systematic way you have to know. Let us bring the change in the internal energy of the system by doing work, by doing some work on it, on it. Let us call the initial state of the system as state A. Initial state is A and its temperature is TA. In the beginning temperature was TA. A means initial. Then initial state of the system as state A and the temperature as TA. Let the internal energy of the system in state A be called UA, internal. Internal energy in the beginning, suppose it was the UA, capital U down a small a. That we can change the state of the system in two different ways. Then what are the two different ways? That you have to understand. Already a given hint I discussed. Then one way, and first way and second way I will tell you. One way, first to six, we do some mechanical work, say 1 kilojoule, by rotating a set of small paddles and thereby churning the water. Okay, means you have heated the water simply. 1 liter. We have done mechanical work, say 1 kilojoule work we have done. How we have done this work? Then just by rotating. By rotating a set of a small paddle, by hand just rotate. Then suppose 1 kilojoule work you have done. And thereby, after that energy release, then you can use by heating the water. All are related, na? All are related. Mechanical energy now you have used as a heat energy. Okay, anyhow you have done the work. Let the new state after doing the work, then there will be change. Let the new state be called B. After doing the work, now new state is called state B, and its temperature suppose change to TV because you have done the work. Then heat is produced. Then this TV will be TB, capital T and B down you can write capital B, capital T down a small b you can write a small letter. Then TB is greater than TA. Then how much change took place? Then TB minus TA. TB minus TA, that is called delta T. Then delta is the change in internal energy. Delta T in the term of change in energy, a change in temperature. Delta T is the change in temperature. Then this delta T change in temperature is called change in internal energy. Okay, delta T, that is equal to TB minus TA. Let the internal energy of the system in a state B be UB. Now in the beginning UA was the internal energy. Now after doing the work, now it became internal energy, suppose UB. Then how much change took place? Then UB minus UA, final minus internal, final minus initial, final minus initial. Always you write like this only. Always talk like that in thermodynamics. Final minus initial. Then UB minus UA. How much change took place in internal energy? Then UB minus UA, and that is equal to TB minus TA. That is the delta T. Correct? Then that is the change in internal energy. Then UB minus UA, that is the delta U. Delta U means change in internal energy. Now, one way I told you. Second way, how it will do the work, that you can understand. We now do an these things. Now do an equal amount, that is the 1 kilojoule. Second way I am talking about. We now do an equal amount of electrical work. Now you are doing electrical work. Same 1 kilojoule work you are doing, but it is the electrical work. Keep in mind, this is again important things. In electrical work, no expansion will be there. Always you keep in mind, electrical work is a special case. Then now suppose you have done same work, electrical work, with the help of an immersion rod, and we have noted down the temperature change. Okay. We find that the change in temperature is same as in earlier case. In the first way, what I have done, because we have done the same work, 1 kilojoule electrical work we have done, but temperature change was the same, because work is the same. Work is same, that's why temperature change was same. This is important things. Either do electrical work or do mechanical work. First case was the mechanical work. You either do mechanical work or electrical work, but you have done the same work, same 1 kilojoule work you have done. Then temperature change was same. Okay. Means in this case also TB minus TA. In the beginning it was A, and later on became TA, later on became TB, then TB minus TA. In this case also we find that change in temperature is same as in the earlier case, means first way, one way what I told you. In fact, experiments in the above manner were done by J.P. Joule between that period 1840 to 1850. That time he did the work. J.P. Joule. That's why unit of energy is Joule. It is given by Joule by this, in the name of this scientist, in the honor of this scientist. And when he did the experiment, he was able to show that a given amount of work done on the system, no matter how it was done, irrespective of path has no meaning, and how work was done, no meaning. What work has been done, that is meaning only. Okay. Then irrespective of path, produce the same change of state, because energy involved is same. Hence how you have done the work, that is meaningless. How much work you have done, that is the important. Okay. How it was done, irrespective, that is irrespective of path, produce the same change of state as measured by the change in the temperature of the system. How much change took place in temperature, that is meaningful. Okay, how did you make the change? That is not important here. This has been experienced by, experiment was done by J.P. Joule. Okay, and he has this thing. He has given one relation also. He equated, after doing the experiment, he concluded that the internal energy U, capital U, whose value is characteristic of the state of a system, whereby the adiabatic work, adiabatic means outside nothing has went, neither matter nor energy went outside, adiabatic, that is called adiabatic work. Then what he told, that he appropriate means now it is appropriate to define a quantity. Now at this stage it is appropriate to define a quantity, that is the internal energy. He has given definition for internal energy U. What is that U? Then he defined the quantity, that is the internal energy U, whose value is characteristics of a state of the system, whereby the adiabatic work W. Okay, if you want to write adiabatic work, the AD you can write in shortcut down the W, AD. Okay, W required to bring about a change of a state is equal to the difference between the value of U in one state and that in the another state. Means delta U is equal to U2 minus U1. Second state means internal energy, final internal energy minus initial internal energy, that is the delta U, and that delta U is equal to W. Means adiabatic work, or simply work you can tell. Delta U is equal to W. Okay, then that is equal to final internal energy minus initial internal energy, means U2 minus U1, that is the W, means work done. Okay, that is, this relation is given by the Joule. This is a very important relation. Delta U is equal to W. W is equal to U final minus U initial. Okay. Therefore, the internal energy U of the system is a state function. Internal energy is a state function. Okay. Now, other things also you have to understand. Now, like that way, temperature, pressure and volume. This also same way you can understand. Same things, that is a T1 minus T2 minus T1, that is a delta T. V2 minus V1, that is a delta V. P2 minus P1, that is a delta P. Okay. Some of the other familiar state functions are is also a state function, because they depend upon the initial and final state volume. What was the initial volume? You have, if you will heat any gas, then it will expand. In the beginning, suppose it was 10 ml, now it became 15 ml. Then volume change took place. 15 minus 10, 5 ml. Means V2 minus V1, that is the delta V. That's why it is also a state function, volume. Pressure also P2 minus P1, pressure will also change. Then that is also delta P, that is a state function. Temperature also will change from T1 to T2. Then T2 minus T1, that delta T, means temperature is also a state function. Okay. For example, we bring a change in temperature of the system from 25 to 35 degrees centigrade. The change in temperature is 35 minus 25, that is the 10 degree plus 10 degree centigrade. Whether we go straight up to 35 degree or be cool to the system for a few degree, then take the system to the final temperature. That manner is not important here, but change is 10 degree. 10 degree. Either you slowly and slowly you heat, or slowly you cool it. Okay, but change is of 10 degree. 10 degree, either final to initial or initial to final. Initial to final 10 degree it will absorb. If it will decrease from final to initial, then 10 degree it will decrease. But 10 degree is important. Minor has no impact. How did you hit? That is not very important. Okay. Then thus T is a state function, and like that way you can tell pressure is also a state function, and it is independent of the route taken. Volume of water in a pond, also you can see a general example. Volume of water in a pond, for example, is a state function. How? Because change in volume of its water is independent of the route by which water is filled in the pond, either by rain or by tube well or by both. Okay, but change took place. In the beginning it was the empty, now it is filled. How it was filled, no importance. Okay, then this volume is also a state function. Okay, then now today I am stopping only here. Next class again I will continue. More things are there I have to discuss. Only one thing I have discussed, work. Now we have to discuss other things also. In the next class I will discuss. Now I am stopping only here. Thank you.